Okay, that looks better. Okay, where do you guys want to start? How far have you been able to get so far on the homework this time?
For me, I was able to get past number 2, but then number 4, um, chapter 10, with the annual capacities and then the unit cost of production, didn't know what to do with those.
Okay. Yep, and that's the most common mistake I see on this one. Oh, we got a few more folks have joined. Nice. So, Unit 3, most of these problems work just like Unit 2 worked. But since you're working with a big array, it feels intimidating. It doesn't need to. Like any problem, and I'll just go ahead and start working through problem 4 here. Like any problem, you just have to decide what your decision array is. So looking at the book, make sure we understand what they were asking for. This is a distribution company that distributes locks. The Lynn Lock Company manufactures commercial security lock at a bunch of different plants. It's got a unit cost of production, and I've gone ahead and typed that into the spreadsheet here. You guys can see my spreadsheet, correct?
No, we can't see anything.
Ooh, I didn't share yet. I was fussing over my recorder so much so I forgot. Let's share desktop 1.
Now we can see it.
Okay, and we got another person that's joined, so I'm going to back up about 15 seconds here. So we're going to look at chapter 10, exercise 4. All this stuff works very much the way that Unit 2 worked, okay? A few people are still doing what is super typical, which is people, when you're trying to work your problems, you keep trying to solve the problem yourself. Don't solve the problem yourself. Let solver do the heavy lifting, okay? So just point solver at the area where you want the solution displayed, and then create a relationship between the data you're given and that solution using a handful of formulas. And if you're doing a gob of formulas, you're probably heading in the wrong direction. So in this case, this is a lock company that manufactures locks at a bunch of different locations: Atlanta, Louisville, Detroit, Phoenix, with a cost of production by location. And then depending on which distribution center it's going to, it's got a different distribution cost. So in this table is the cost to ship the locks. In this over here is the cost to make the locks. And this is the capacity that each one of these production locations has. So Atlanta can only make 18,000, whereas Detroit can make 25,000. Okay, so this is what we know about the company. So the question is, which location do you want producing, and where do you want to ship it to? Okay, so the solution is going to be 4 down, so my 4 manufacturing locations. And I'm going to slide across. Oops. If I can get coordinated this morning, I'm going to create an array that is the same size and shape as my data. Okay? I very much like, and those of you who have adopted this practice, hopefully you see that it's helpful. This is where my decision variables are going to be. And what this is, I'm going to say decision variables. I'm going to call this quantity by location. So whereas this data table up here is in dollars, it's in cost. Okay? And in fact, I'm going to reformat this to make this easier on you guys. So this is in cost, right? Even though in the book they didn't make it super clear. If you read the problem, these are costs. These are shipping costs, and these over here are production costs. This down here will be quantity. Based on these costs, how many locks do I want to make at each location and ship to which location? Okay? So I'm going to copy my headings again.
Excuse me, can you zoom it in a little bit?
Oh, I can. Is it a little small?
Yeah.
Well, I see I can zoom in a little bit. I gotta move myself out of the way. here. Whoop, that's the wrong way. There, is that better?
Yes, much better. Thank you.
Wonderful. Yeah, thank you for asking. So my decision variables is the quantity I'm going to do by location. So first, I'm going to copy my headers, and I'm going to copy these. Okay, and these are going to end up being quantities. Okay, and I see that my capacities by location is in thousands. So just like every other time we do a problem, it's super important. Go ahead and put some starter values in here, okay? It's it may not seem like a big deal, but you can't tell if your formulas are working if you don't put something in here. And I like to just put something in there that's roughly the same order of magnitude as the solution I'm expecting. There. So that is my starter values I'm going to put in there. Okay. Now, starting to think about the problem, it wants to know how much do we want coming from each distributor in the following year. And we have to determine the least costly way of producing and shipping locks from those plants to those distributors. But we know a few things, okay? So we know that there's a capacity limit by production location, and there's a demand by ship to location, okay? So I'm going to say that over here, I'm going to say produced is the sum of everything that was produced out of Atlanta. Okay, and I abbreviated Atlanta here, Louisville, Detroit, and Phoenix. So that's the sum of that. So in a little while, when I populate Solver, I know that I can't let these produced numbers exceed the capacity by location. Okay. Then I've got a quantity that got supplied by location. Okay. So just using our intuition before we keep building the model. Okay. So just with my dummy values, I see, aha, Tacoma with my dummy values got supplied with 6,000 locks. Okay. But the demand at Tacoma is 5,500. So after I populate Solver, I know that it's going to change some things so that this supplied number matches this demand number of 5,500. In the case of San Diego, my dummy values are under supplying. My demand is in San Diego, and so on and so forth. Over here on my capacity, none of my capacities got exceeded, so all these are going to get bigger. Okay, so these are costs, and these are costs. They're both costs, right? Okay, so in this case, while this looks big and intimidating, a lot of things in Unit 3 have fewer formulas to build than we did in Unit 2. So I'm going to say that my objective is to minimize total cost. I'm going to build a formula right here to do that. I'm going to shade it light green. I'm going to put a box around it so that I can find it easily. Okay. In a minute, I'm going to remember that these and these are constraints, okay, that I need to relate to. We're ready to build this formula and then build Solver. So for folks that are comfortable with some product, I'm going to do it this way, and then I'll show you why it works and how it works. If I take all these costs in this array, and in Unit 2 we only did arrays that were 1 wide. In this case it's a 4 deep by 6 wide array, and I'm going to multiply that by the quantity I planned at each location. This will give me just the shipping costs to start with, okay? But just so you can see how these formulas work again as a refresher, okay? So this is a dollar amount. Using my dummy values, I come up with $87,150 for just the shipping component of this. As a refresher, what sum product is doing is it's taking the first item in the first array times the first item in the second array, and it's adding to that the second item in the first array times the second item in the second array, and adding to that the third item in the first array times the third item in the second array, and so on and so forth. Now you can see why the sum product formula is so helpful. I'm going to do this for you and leave that in there just so you can see that's what the formula is doing. As soon as these arrays get a little bigger, the sum product formula is way more helpful because I'm pretty particular and I pay really close attention to details, but even I probably can't build that formula the manual way without a typo before I get through an array this big. Okay. So I already said this is what we picked up so far is only the shipping costs. Let's add to that the production costs. So here is where we calculated what we chose to produce. Okay. So I'm going to do a sum product of the calculated production, comma, and I'm going to multiply that times the cost of production by each location. I'll leave all this highlighted for just a second. Does everybody see the two different array sets that I'm doing the sum products? Doing a sum product of this big array of shipping costs times this big array of shipping quantities plus the sum product of the production quantities times the production costs. Hit enter, and using my starter dummy values, I've got 1.77 million as a total cost. Okay. You know what? I'm not super interested in all these decimal places. I'm going to make that a little smaller. There. Okay. Now, believe it or not, that's it. That's the end of building formulas. Okay. So now what do we do? Well, we load this into Solver, and it works very similarly to how you've done it before. You know what? I need to change the size of my screen a little bit here. Sorry. Y'all probably can't see my problem here, but my screen recording software is covering up part of my Excel page. There. So now I go Data, Solver, okay? And what's my objective? It's this 1.7 million. And I do want to minimize it. Whoops, forgot to reset all, because I've used this sheet before. All right, D21, I'm going to minimize by changing the variable cells. I'm going to come over here and I'm going to select this whole array, all these numbers all at once, okay? Subject to the constraints, I'm going to add these in. Since this is the one I can see at the moment, I'm going to say that these produced by location must be less than or equal to the capacity by location. I'm going to add another one and say that my supplied by location, and I'm going to claim this as a true inflexible demand. I'm going to say that it's equal to this demand by location. And I think that's what the problem is looking for. If it's not, it won't converge for me and I will learn something. Okay, and that's it. I think that's all I have to do for this problem. So I'm going to click Solve. And you see it had to think quite a bit before it got to a solution that it thinks is workable. I'm going to click OK. Now, since it thought for so long, well, we got a hand raised too. All right. So what's our question?
Yeah, my question is, how do we know which algorithm we use? How do we know if we use linear programming or non-linear?
So my answer is going to frustrate folks that are on a Mac. If you're on Apple, you don't. start with nonlinear, and if it won't run, try the other one. Solver does not work 100% correctly on an Apple product, and I know most of my folks in Rwanda and 100% of my international students are on an Apple. So if you expect, so just like in Unit 1, we did that series of curves on the tractor import company. If you expect that curve to be cyclical or to be a smooth curve, you can pick the linear programming solution. If you expect the curve to have a bunch of jumps or gaps in it, you need to pick nonlinear. If you're on an Apple, I almost always start with nonlinear as my solution and see if it will run. And unfortunately, that's just the situation that you're in with an Apple. Excel does not run quite correctly. It's not optimized for the chips that Apple chooses to build their machines with. So I apologize, that's a little bit of a frustrating answer, but that's basically where we are, unfortunately. Okay. So let's see what we calculated here. And since that took so long to solve, I'm going to click Solver again in a minute, but I'm going to look at my numbers that I've got. Some of you have already been doing this. You can force it and say, hey, I don't know how to ship 9,599.9 locks. So I'm going to force all these in this block to be integers. You can add that requirement. You can also approximate it just by changing the format here. I'm going to change the format so that it just doesn't show me the decimal places. So we can see how many locks were supplied by location. Okay, and these types of problems often have more than one correct solution. So if you're working with a buddy and talking through this, and you say, "Hey, instead of 2.78 million, I only got 2.72 million," and this block looks very different, as long as this constraint, the idea that you supplied the same number of locks that was demanded, and you did not exceed the production limits, it is possible that there's 2 or 3 solutions that are pretty close to each other. Okay, it annoys me too, but it is what it is. But I'm gonna click Solver again. Nope, and it likes that. It stayed there. So I do know there is a solution that's slightly lower than this number, but we've met our constraints in this case. So we have not exceeded capacity anywhere by taking a quick look at those numbers. Let me format that a little differently.
On Solver, you have it max to max it. Does it matter if it's to minimize or to max it?
It's supposed to be min. Did I double click it? Oh, I did. That's why I'm getting a slightly different number. Thank you for catching that. So we're supposed to minimize cost. I thought for a long time. It's pretty happy with that. I might click it one more time. Okay, so that's the answer I got when I developed the answer key. Thank you for catching that. That's an easy mistake. But you can see, while it looks intimidating, there's actually very little math on this page and only a couple of constraints. So if we go on to the part B, suppose that the unit costs at each plant were $10 higher than the original figure. What change in the optimal distribution plan would result? What general conclusions can you draw for transportation models with non-identical plant-related costs? That's a really fancy way of saying the cost of production went up. So I'm going to click Move or Copy on my tab. Click Create a Copy. Drop it before 10.7a. So here's our copy. I'm going to rename it. This is B. Okay, so it's just asking, the what if. What if my costs go up on a per location by $10? So I'm going to call this cost of production for part B. And I'm going to make it wrap. Put the word part in there. There. Now, this is where I like to be very simple. I'm a simple guy. So if I add 10 to that, I'm going to format it back as $1 again. Here's my new costs by location. So the super efficient way of doing this is, I think even on a Mac, Solver copies the Solver selections. It does. So all the constraints I had in my original tab are already in there. All my references are already in there. But I just have to change a formula. So I'm going to hit close. So this formula down here, my total costs, make this so you can, so you can see both of them. There we go. So this formula that we did was referring to this cost of production. I'm just going to grab that and move it over to my new cost of production. Hit return. Now I'm going to go to Solver and just run Solver again, because all the references are already in there. The constraints are already in there. Just what my costs are predicated on is different. Click Solve. Say OK. Okay. It doesn't look like it changed where anything gets produced. So my guess is, and here's where I like to explore some things, because all of a sudden I'm skeptical. I think maybe our shipping costs are so significant that they are overwhelming our production costs. $3 million. Nope, it's the other way around. Our production costs are so significant they're overwhelming our shipping costs. Interesting. So that's the part B for this one. And all of a sudden I'm wondering why I like to assign this problem, because it's not very interesting. Interesting. Okay, questions on that? Okay. So for 10.2, it's approach it the same way that you did the first part of this 10.4. One of the critical things to do when you have a data set like this that is missing values is put in a replacement value. So since this is going to be a planning of a purchase and it's going to try to minimize cost, I'm curious, let's see if anybody draws the correct conclusion. What is Solver going to assume a blank value is?
A 0.
A 0. So does that mean that from supplier number 4, commodity number 1 is free? That's what Solver would think it is. So anytime you're minimizing based off of a provided data table like this, you need to put a value in here that is an order of magnitude bigger than your biggest current value. What I was taught is get in the habit of using a number like 9,999. Okay, that does two things. It makes sure that Solver knows that that is not free. In fact, it is completely unavailable from that particular vendor. And if this is a great big data table and you've had to clean the data by putting in dummy values like that, it's super easy to find again. It's because most people that take this class, it's simply a requirement. You're heading into a different part of business. But if you end up in data science or sales and operation planning or in finance that you're working with large data sets, you may end up working with a data set like this that has missing values, that instead of being 5 columns wide and 5 rows deep, it's 10,000 columns wide and 200,000 rows deep. So you would have replaced your missing values by using the find and replace command, and you would do yourself a terrible disservice if you picked a number that might easily blend in with the others. So pick a great big number that's like all 9s or all 7s. So it's super easy to spot. Okay, and you set this up very much the same way you did the other problem. I'll show you the setup, and then I want you guys to wrestle with it. You're going to have a decision variable set that is going to be the same size as your data set. Okay, and these are going to end up being quantities. And you're going to create a formula that creates a relationship between this data and these quantities, and subject to the constraints of the demand, okay? Just like we did on 10.4. All right, y'all let me get away with just setting that partially up for you like that. All right, so what's the next question you guys have? Have you tried to tackle 10.7? 10.7 part A is to do the manual way that lots of companies plan their shipping and production today. They've got some rule of thumb they apply that works pretty well, but Solver can optimize it even better. And then Chapter 9, Exercise 14 is actually the same approach as Unit 2. It's just a really tough problem, which I will set up for you, but that's one I'm curious to see you guys wrestle with. But I'll spend a little bit of energy setting it up if you want me to. So what do you want me to spend a few minutes on next? Or I'll do this. You know what, I'll work at least part of this manual version for you, and then I'll set up Chapter 9, Exercise 14, and see what questions come up from that. So the first thing I'm going to do, a lot of companies that are doing, so lots of stuff in manufacturing has a yield component. In fact, everything I know of calculates a scrap number or a yield number or a spoilage number in some fashion. So if I'm a machine shop and I'm taking a big bar of steel and I'm cutting it to be something different, I don't end up sending, if that bar of steel weighed 40 pounds when I got it, and I make a machine part out of it, it only weighs 28 pounds when I'm finished machining it. So I had 12 pounds of scrap, okay? Me personally, I've been in the food manufacturing and beverage manufacturing industry for 31 years. So the idea that I have a shelf life for what I'm producing, so that when the consumer, like right now I make a lot of canned beverages. Let's say I made a can of Alani Nu energy drink. I don't know if y'all are familiar with that one, but it has like an 18-month shelf life. Well, I produce it in January. It may sit in my warehouse until February. Then it's in the trucking chain until March. And it finally makes it to the grocery store shelf in April. Well, 4 months of the 18-month shelf life has already been used up before it ever hits the shelf for you to buy it. Then it sits in the grocery store for a month or two, depending on what type of grocery store it is. Now it's June, and by the time you buy it, it has a Best Buy printed on the can that now shows it only has about 11 or 12 months left. Most American consumers buy things in advance, so it sits in your pantry for a month or two. So by the time you consume it, it may be down to only 8 months left of shelf life. Other parts of the world tend to buy their consumables more fresh, so this is a good example of fruit and what you lose in trucking over a very short period of time. Okay, so let's do this. So these percentages are my yield loss. This is the scrap that takes place based on shipping each of these items on each of these trucks. So the trucks are different than each other. Maybe it's a different driver, maybe it's a different type of truck, maybe the refrigeration system on the truck is different. I don't know. I don't know how they built the assumptions for that. But this is the scrap rate. The inverse of a scrap rate is your yield, okay? So you have your yield loss, and if I want to come up with my yield, I just do 1 minus that number, okay? So 88% is my yield. So if I ship grapes on truck number 1, 88% of those grapes will make it to the market to get purchased, okay? So I'm gonna copy that formula and I'm gonna call this my yield table, okay? That's how well stuff makes it to market. Okay, I'm gonna come down here and I'm gonna have some decision variables. I'm gonna make a note that I'm gonna say, this is my manually loaded data. So I'm gonna do this by hand. I'm not gonna let Solver do it right now. That's something that you guys are gonna wrestle with on your own. And my decisions is gonna end up being a table that's the same size and shape, 2, 3, 4, as my data up here. So I'm going to highlight it just like I do when I have Solver do it. So I'm going to manually load this with what I think the solution is, okay, based on this yield table. I know I've got a couple of constraints, even if I'm doing this manually, okay? The constraints are, I have got a capacity right here. So I'm going to say that there's some number that got loaded onto this truck. So I'm going to add this up. You see, I'm not putting dummy variables in yet. That's because I'm going to do that in a minute as the actual exercise. And then I've got an in stock right here that I need to put on each truck, right? So I'm going to say down here, how many tons did I load? These are tons of fruit, not pounds. Okay. All right. Now, and then I have, based on that, I've got some calculations. So I'm curious to know how much of this stuff made it. If you'll bear with me for a second, I'm going to make sure that the formatting is blanked out here. Okay. So this is, I'm going to manually select. You know what I'm going to put? I am going to put some dummy numbers in here just so I can see if my formulas are working. Just 1 ton each. Okay, there we go. So that makes sense. Then I have an objective of, I want to understand, how much of each of these items arrived at its destination. Fruit that arrived, I'm going to call it that. And I'm going to do some calculation here. I'm going to outline this just so I don't get lost while I do it. So if I say that I loaded 1 ton of this fruit on here, of grapes on here, if I multiply that times the yield, that tells me how much of that made it to market. Fruit that arrived, let's see this, at market. Okay, this is my grapes, my peaches, my bananas. Okay, and then I'll have a total that made it there. So I'm just going to copy that formula. Whoops. Sorry, y'all. There we go. I'll be lazy and I'm going to copy this. So that's the, so you can already see from an intuition standpoint, I loaded 3 tons on a truck number 1. Because of the yields, only 2.7 tons made it to market, okay, because we have a spoilage rate on the truck. Okay. And we're just going to sum these two and say, hey, I want to know how many grapes actually made it there, how many peaches, and how many bananas, right? Okay. And then we're trying to maximize our sales revenue, right? So when you do this with Solver, this is going to end up being your objective. You want to maximize your dollars. So, and I'll go ahead and let you guys peek behind the curtain. The rule of thumb we're about to use to load these trucks, while super common in lots of industries, it attempts to maximize the eaches, how many grapes, how many peaches, how many bananas made it to a destination. It doesn't take into account up front, anyway, did that actually maximize your profitability, or did that only maximize how many pounds you can move? So I'm going to do a sum product of the fruit that arrived, okay, not what I loaded, what made it through the system, times the price per fruit. Okay, you'll see that. Fix that formatting. Less decimal places. They're not that interesting. Okay, so that's the setup for the manual one. Now in the manual version of this is kind of funny, okay? So this is real world stuff, right? So what I do is I look through my yield table for my best yield. And I say, aha, I have found it. So truck number 1, shipping bananas. I'm going to put a bold on this so I know that I'm using this. That has the best yield of anything in my system. So I take a look and see and say, okay, I need to ship 81 tons of bananas. Truck number 1 has 40 tons of capacity, so I can't put all the bananas on truck 1. So what I'm going to do is say, I'm going to take out this dummy value and this dummy value, and I'm going to put as much as I can on truck number 1 of my bananas, 40 tons, right? Based on just my eyeball, on this little table. And then I go back to my table and say, what's my second highest yield in this table? Oh, it's still bananas. Very cool. So it's bananas, and this time it's on truck number 2. So I'm going to click bold on there, so I know I'm about to use this. Truck number 2 has 50 tons of capacity, and how many tons of bananas do I have left that I need to load? Okay, so I'm actually going to get rid of the rest of these dummy values. These are going to confuse us. Okay, so I can see that I've only loaded 40 tons of my 81. If I wanted some help doing this, you know what? I am, in fact, going to do this so you guys can see it remaining. So I'm going to say that out of what was in stock minus what I've loaded so far, here's how many I have left remaining to load. So I've got 41 tons left I need to load. Truck 2 hasn't hit capacity yet, so I'm going to put all 41 on it. Ooh, wonderful. In fact, I'm also going to give you a column here for remaining capacity, if I can spell it. Good grief. I can tell it's a Monday. So this capacity minus what was loaded, there, that'll just help me do this manual loading. I can see how much is left. So I've got 9 more tons I can put on truck number 2. Well, let's go back to my table. What's my next highest yield? Oh, look, it's still bananas. Okay, y'all see a pattern forming? But do I need to load any more bananas? Oh, I don't. So I'm going to go ahead and bold out the rest of my bananas. And out of the stuff that hasn't been loaded yet, what's my next highest yield? Ah, it's 90% on peaches. So I'm going to load some peaches now. So peaches, I'm going to come over here, and I'm still in truck number 2. And part of the philosophy of this is you just move down the line of your available trucking. So I've got 9 tons left available to put on truck 2. Bingo. Now truck 2 is full. And I used 9 tons of my peaches, and I have 53 more tons of peaches to load. Okay. So I go back to my yield table. What's my next highest yield? Oh, look, it's grapes. Ooh, and grapes has got a couple of different things. Oops, and I made a mistake. So I loaded this, and you're about to see why this method is prone to error. I saw this 90% of peaches, and I put it on truck 2. Well, that 90% was for truck 1. Whoopsies. So I'm actually going to delete this. I'm going to bold out the rest of truck 1 because I actually only have room on truck 2. Oh, okay. So truck 2, my best remaining yield is this 88% of grapes. Okay. So I'm going to come over here to truck 2, and I can put 9 tons of grapes on there. Oh, now truck 2 is full. So I'm going to finish bolding out truck 2. Now I'm down to truck 3. What's my best yield? Well, it's peaches now. So I'm going to say that peaches, I got 62 tons to load. I've got 55 tons available. So I'm going to put 55 tons on truck 3, and now it's full. Okay, great. So I'm going to pull out the rest of truck 3. Now on truck 4, what's my highest yield? Well, now it's peaches. So I'm going to put as many peaches as I can on truck 4. Oh, I only have 62 tons left of peaches. Oh, I take that back. I only have 7 tons left of peaches. So I put all those on truck 4. And my remaining yield is grapes of 82%. So I'm going to go over here and load some grapes on truck number 4. And I've got 57 tons. I got 48 tons left to put on there. So I'm going to put 48 tons on there. And you can see a couple of interesting things cropped up. I didn't fill truck 4, did I? So using this methodology, there's some flaws in my thinking, but I managed to get $212,000 worth of product to market. What you're going to do, I am going to copy this tab, create a copy, put it before that one. Okay, now on your own, you're going to use Solver, and instead of, so you've already got dummy values in here that was your best guess, right? So you're going to go Data, you're going to go Solver. I'm going to reset all these, say OK. So you're going to select as the objective sales revenue. By changing the variable cells, pick all these cells. Subject to the constraints, put constraints in on how much each truck can hold, capacity versus loaded. Okay. And say that tons loaded must be less than or equal to, so loaded must be less than or equal to capacity, and tons loaded must be less than or equal to what was in stock. And you want to maximize your sales revenue, and you guys can do that on your own. And what I really want you to do, especially those of you who are on this call, is spend a little bit of mental energy describing, hey, Solver did a better job than Professor Jim did in these areas. And yes, we know that this cool rule of thumb gets us pretty good product to market. And I think you're going to be surprised at how close this is to what Solver does. But Solver will make a few different choices to try to get the dollar signs up instead of the yield first. So when you make some commentary, make some additional commentary on, you know, when I did it by hand, here's how many grapes, peaches, and bananas made it to market. Versus when Solver did it, here's how many made it to market. Okay, is that fair for you guys to tackle that on your own, you think?
From my end, yes.
Yes. I used to do this every time. So when I first taught this class, I put a screenshot of the book next to anything I gave you guys. I had a student actually comment that it was kind of dumb, so I quit doing it. Okay, so now you just got the, let's rename. This is actually B now. Bing, bing. Okay. All right. You guys want to see me set up exercise 14 a little bit? And I won't 100% solve it for you because it is a really challenging problem, and I'm curious to see who can really think through this. But it's a pretty cool multifactorial problem. So you've got a boat that has 3 storage holds that have a bunch of rules about what you have to do to make sure the boat floats correctly. And you have a bunch of different commodities and that have different characteristics. This uses the exact same mental approach as the homework problem for the investment bonds. How much of each investment utility do you use? Because you have a commodity that has multiple characteristics. It has a certain weight, amount available. It has a weight, what the volume is per ton, and what the profit is per ton. And then you have constraints based on the boat, including how do you balance the boat. Okay. So for decision variables, the first thing you do is you build the boat. Okay. I am going to put it, Where do I want to put it? Make this easy on you guys. I'm going to put the boat right here. So the boat can hold up to 4 commodities in each hold. So we have a rear hold, a center hold, and a forward hold. And for my non-native English speakers, a hold is a storage area on a boat. And please call me out on that. Anytime I use an interesting word that's not translating perfectly, that's great. So these are my decision variables, okay? These are tons that I'm going to put in each storage area. This is the rear storage area, the center storage area, and the forward storage area. And this is the quantity of commodity 1. Whoops. I know I already said it, but I'm having a Monday today. Quantity of commodity 1, quantity of commodity 2, and quantity of commodity 3. Okay. Like always, I mean, this is the tons available are in the thousands. So I'm going to put numbers in here that are kind of thousand-ish. Okay, so I can see if my formulas are working. Okay, so as you start to build this and start to think through this problem, this is one of the times when a problem gets more complex like this. Definitely do this a piece at a time, a small piece at a time. So one of the first things I'm going to say is, I mean, at the end of the day, what am I going to try to maximize? Okay, I'm going to put it right up here at the top instead of, you know, at the bottom like maybe you might do normally. Total profit. So this is the profit that I get from, you know, shipping my tonnage, and that's the terminology the book used on the profit per ton. So I'm going to say I've got a total profit I'm going to come up with. I'm going to put it at the top of the page, which is a little unusual, so I can keep my eyes on it. Okay, since I'm thinking about that, I'm going to say I'm going to have some profit contribution and build some formulas right here. So based on how much of commodity 1 ends up on the boat, I would multiply that by the profit per ton, and commodity 1's value would go, you know, right here. And then what commodity 2 does right here, commodity 3 does right here. And if you add these together, that's your total profit, right? But we have some constraints that we also will want to do. We're going to have some sum of the commodity I've put on the boat so far. When you run this with Solver, this sum for commodity 1 must be less than or equal to what was available for commodity 1, right? Great. Okay, then we have a sum that we would put here of how many tons we have loaded in the rear. I'll give you all a tip by put one formula in there. So how many tons were loaded in the rear versus how many tons are loaded in the center versus how many tons are loaded forward. We also know that these commodities have different volumes they take up based on tons. So let's calculate. We're going to have some volume that got loaded into the rear, right? And I'll give you one formula. So if I loaded 3,000 tons, and I know that that commodity has a volume of 40 something per ton, whoops, 3,000 times that 40, then this is the volume I've loaded in the rear so far, right? Okay. Now, and I did this on purpose. I didn't make it big enough. All right, now I did. So the volume in the rear based on our dummy values is 132,000. Our volume capacity is 120,000. So you have two different types of constraints on each piece. So you have a weight constraint that you're going to have to compare to the weight capacity. Okay. You're going to have a volume constraint. You're going to have to compare it to the volume capacity. And you can see the dummy values I put in. The volume, the weight in the rear is over, and the volume in the rear is over, okay? It'd be hard for you to do, personally. It's not hard for Solver, as long as you build this constraint and this constraint, and you're asking it to maximize profit. Now, what else do we have in terms of constraints that you're going to have to tackle? You have a couple of balance limits. So the maximum the center can have as a percentage of the total is 60%. So you're going to have to calculate, and this is weight, right? Let me make sure. All right, I got to look at the book real quick. Yeah, it's weight. So you're going to have some formula you'll come up with for center. What are its tons as a percent of total? And you'll need to compare that. In fact, I'll do this for you. This is where you've got to come up with some formulas to create some relationships. And even with this much setup and help, this is still going to feel hard. Then the forward can be no more than 10% different than the rear. The most common mistake I see is people try to create a formula here and they accidentally make the forward area 10% of the rear, okay, instead of 10% different than the rear, okay? So I'm going to type a logical formula here and say that in order to come up with a formula that will calculate forward percentage difference from the rear, I'm going to reference the cell that's the tons in forward minus tons in rear, and that will be divided by the tons in rear. And if you express that in a percentage, that will give you the difference between the two, okay? So I'm going to have a forward percent different than rear and build a formula for it. In fact, I'm going to move this formula where it's in line with that. So this logical piece I just talked through, you're going to build a formula that does that and put it here and then compare it to this constraint. Okay. So this is, in this particular course, this is the biggest model you'll build in terms of how many total constraints you've got to factor in. Okay. Don't get ahead of yourself and make up new constraints. You've got enough already. You've got a weight capacity by bin. You've got a volume capacity by bin. You've got a limit in terms of how many commodities are going. You don't have a demand by bin. That doesn't exist, so don't create that out of the blue. You do have limitations on tons by bin, volume by bin, how much can the center be relative to the other two, and how much can the forward be relative to the rear. All right, so this, you should be able to grind through this and then move on to part B. So before I talk about part B a little bit and plant some seeds for you guys, questions on this kind of big convoluted setup. And it doesn't look like it to some people, but this is basically just a mixing problem. It's just like the fertilizer problem. It just has more constraints. All right, so when you go to part B, what it asks is, suppose each one of the cargo holds could be expanded. Which holds and which form of expansion, weight or volume, would allow ICC to increase its profits on this trip? And what is the marginal value of form of each expansion? So what I want you to do is after you build this and you run Solver and you come up with a total profit, copy the tab. And as a reminder, folks that are on a Windows machine, you would right click on your tab and you'll get an option for move or copy. If you're on a Mac, push and hold the control button and click the tab and you'll get this menu to pop up. and you select Move or Copy. Create a copy, move it to the end, and click OK, and you'll get a copy of your work. When you're looking at Part B, look at which one of these maxed out. Is the volume in the rear at the maximum of the volume? Is the weight in the rear at the maximum of the weight? And put some comments in there saying, I'm going to change my limits and my constraints over here. You can even change these, the weight balances. And what I'd like you to do, makes it easier to see, is if you decide to change, say for example, I decide that the forward cargo hold needs to be able to hold more total weight. So I want to change it to 4,000 to see what the new solution is. Make it bold and italic, okay? If you're on a Windows machine, Control B-I does that. If you're on a Mac, Command B, Command I does that. I'm going to change it back. Okay, and then you would run Solver again. And play with it in Part B. Change one thing, run it, make a comment. Change something else, run it, make another comment. Really spend some time playing with this because this is your chance to take a lot of what you learned in Unit 2 and do it all at once and just really, really fidget with a solution. All right, I know this has been a lot and I talked a lot and we're at about an hour. Are there questions any of you had that I have not started to address or anything else you want to see before you go attempt this on your own? And even though you got part of this for free, you can still send me questions in email. I want you to learn this stuff. Like I said in one of my videos, my goal in life when I teach one of these classes is that every single person get an A in this class. I have zero interest in seeing anybody get less. I don't care about a bell curve. What I care about is you got a chance to learn something that you may encounter again in life and do really well. So questions, comments, concerns? I gotta write something down. Okay, let me take a quick note before anybody drops off. Let's see here. I've got Eves, IKEA, Denise, Jesse on here. Okay, well, if you don't have questions, I'll email out this Excel file within the next 10 minutes or so, and I'll upload the video to YouTube. For folks that have not been on a tutoring with me before, YouTube has changed some of their security protocols, and it will take several hours for an hour-long video to upload and get approved. So it'll be a little later today before I can send the YouTube link out, but I will get that YouTube link sent as well. So I will send you this file, and I will also send you a YouTube link when it's ready. All right. Well, if there's nothing else then, I hope you all have a great week and hit me with your questions if you get more.
Thank you.
Hey, thank you all.
Thank you. Bye.
Have a good day.